All right, in this video we're going to be talking about thermochemistry, which is looking at what in chemistry makes changes in temperature happen. So first of all, we need to look at some terms to know. I got to change my tools where they're docked because I got them covered up. All right, so first of all, what is energy? Energy is the ability of a substance to produce changes in itself or in its surroundings. And we measure energy in either joules or calories. So the correct scientific unit is joules. Calories is a common one that you may be familiar with. Of course, you're not familiar with calories little c like scientists use. You're familiar with calories big C, which is actually 1,000 calories. So if you're eating a hamburger or whatever and it's 500 calories, big C calories, it's actually 500,000 little c calories. So a calorie or a joule both are fairly small in terms of energy. So oftentimes we'll talk about kilojoules instead because that's a bigger unit that's more appropriate in chemistry. Temperature, spelled measure wrong, sorry. Temperature is the measure of the average kinetic energy of the particles in a material. So we already looked at with gas laws, the temperature has to do with how fast the individual particles are moving. And in thermochemistry, we can measure in Kelvin, but we can also measure in degrees Celsius because we're looking at the difference in temperature, not the actual temperature. And so the difference of a Kelvin temperature and a Celsius temperature will be numerically the same. And then heat, the term heat refers to energy flowing from one place to another, and it again is measured in joules or calories. When we are looking at why do reactions cause temperature changes, it's because whenever you are reacting something, you are breaking old bonds and making new bonds. Just like breaking a rubber band, when you stretch out a bond and break it, that requires energy. When you make new bonds, it's harder to come up with an analogy for this, and energy is released because electrons are going into more favorable orbitals. If that wasn't happening, if electrons didn't go down in energy to make a bond, the bond wouldn't be forming in the first place. Okay? So if I look at this reaction, which is the reaction between hydrogen and oxygen to make water, this reaction releases energy, and we can see why. Okay? So if I break each bond that I break between hydrogen atoms requires 436 kilojoules of energy. To break the bond with oxygen requires 498 kilojoules of energy. Each bond that I make over here will release 464 kilojoules of energy. So if I look at the total energy required to do this, I have to break hydrogen bonds, which requires 436 kilojoules, and I have to do that 2 times. I have to break an oxygen double bond, which requires 498 kilojoules, and that I'm only doing once. Both the whole double bond is all part of this. And then releasing, I am making 4 bonds that each release 464 kilojoules of energy. So if I want to know what the total energy change is, I take the amount of energy I put in, which is 1370. So 1370 is the 4 times 464, and I subtract, how that works out to 1370, I'm not sure what I did. And then you subtract, or sorry, put in, the 1370, sorry, is the total required, so that's the amount put in the purple one, the other color coordinated. So 436 times 2 plus 498, I put in 1370 kilojoules. I'm going to release, taken out, so out is negative, 1856, which is 4 times 464, and I'm going to overall have negative 486 kilojoules taken out every time I do this reaction. Now, all of these are on a per mole basis, not actually on a per bond basis. Okay? So this is also this negative 486, that would be per 1 mole of oxygen made, so per mole of this happening. Reactions, as you've seen in your exploration, hopefully can do one of 2 things. They can either release energy so the surroundings warm up, or they can require energy. In chemistry, a process that requires energy to happen is called endothermic. And so in an endothermic reaction, you have to put more energy into breaking bonds than you get back releasing bonds. So what happens is you start off with your reactants here, and then some energy is given to make some intermediate. The bonds are broken, bonds are reformed, but you end up higher in energy than you started. So you have to take energy in, and that cools the surroundings. An exothermic reaction is just the opposite. Again, energy always has to be put in to start, but then when they fall down and the bonds are remade, you get much more out of it. And so because there's not as much energy stored in the bonds, now it's going to be released to the surroundings, and so the surroundings temperature will increase. When we are working in chemistry, we use this quantity called delta H, which is the enthalpy change. And enthalpy change is the amount of energy that goes into changing the temperature of the surroundings. So the reaction can change by actually more energy than the actual enthalpy change, because some of the energy is going to go into making the system expand or contract. Okay, and we have a formula here that delta H is equal to the enthalpy of the products that you start with minus the enthalpy of the reactants that you had to begin with. When we have an endothermic reaction, as we've talked about before, delta T for endothermic reactions will be negative. The temperature will go down. Delta H is positive, okay, because you end up higher in enthalpy than what you started with when it's endothermic. But that energy had to come from somewhere, which is why the temperature has to go down. For exothermic reactions, energy is being released to the surroundings. So the surroundings go up in temperature. The enthalpy goes down. Okay? So the enthalpy of what you have is lower than what you start with. Sorry, my box is a little bit out of adjustment, whack here. So standard enthalpy change. When you're doing a reaction, depending on the conditions you do the reaction in, how much you put in, what the pressure of the room is that day, what temperature you're doing at, the amount of energy that your reaction can change by actually differs. And so in books or on the internet, they only list what the standard enthalpy change is, what happens, what's the enthalpy change of that reaction when it's done at 1 atmosphere pressure and 25 degrees Celsius, because those are what room conditions are generally close to. Okay? And for those given amounts. Okay? So when you look up a standard enthalpy change, they're given for a certain number of moles of each substance in the reaction. But when you do it in lab, you might be using a different amount of stuff. Okay? So we're going to use this formula to go from one situation to another. Okay? So here's an example problem. We want to know how much heat will be released when 6.44 grams of sulfur reacts with excess oxygen. So we're given a reaction that shows that sulfur reacts with oxygen to make sulfur trioxide, and we're given a delta H of negative 791.4 kilojoules. This delta H here can mean that it's either per 2 moles of sulfur, because there are 2 moles in the reaction. If we were looking at oxygen, it could be per 3 moles of oxygen. If we were instead of looking at oxygen, because there's a 3 there, it could be per every 2 moles of sulfur trioxide. So when we're looking at this reaction, the delta H with the little 0, delta H naught is how we would say that in science. That's our negative 791.4 kilojoules. The moles from the reaction, that happens for every 2 moles of sulfur. Okay, so that's what our standard enthalpy change happens. We want to know how much delta H, what would the enthalpy change be for 6.44 grams of sulfur? Well, first, since we're comparing moles to moles, we have to get that grams into moles. Well, 6.44 grams, hopefully you can do the math to figure out how you get that, is 0.201 moles of sulfur. And now that we have this set up as a ratio, you can cross multiply and divide to get what the answer is. So you should try that out on your own and make sure you can get that answer of negative 79.5 kilojoules. Okay, so here's another one that you should try on your own. here's the answer. See if you can come up with the answer. If not, come and complain about it tomorrow. All right. The next thing we want to talk about is something called Hess's Law. When you're dealing with energy changes, it turns out it doesn't matter how you get from point A to point B. The only thing that matters is how big a difference is the point A and B. So if this woman here was to go across the floor, and I won't let me because it won't let me follow the path, and end up here on this platform, she's only gone up just a little bit. So she's only increased her height by this amount. If she takes this weird convoluted path that's supposed to be hidden from your eyes, but for some reason isn't, up the stairs, across the platform, down the stairs, down the ladder, she still increased her height by just that little amount. So even though she had to go way up and come way down, the amount of energy change is only just that little bit. You might be asking me, why does that matter? Who cares? We usually don't go upstairs and go downstairs and then down ladders and everything else. Well, it turns out in chemistry it matters a lot. Okay? Because in chemistry, you can very easily look up the enthalpy changes for some reactions because they've already been done. But other reactions might not be there. You might want to know what it is. If you can find ways to cleverly combine two different reactions to make, or more, I mean, you could have 10 reactions. If you have a way to cleverly combine different reactions to get what you're looking for, then whatever you had to do to those reactions to add them up is going to be what you have to do to their enthalpy changes to add them up to get the overall difference. Okay, so there's some steps for doing this. Okay, so again, we're given, we want to get this reaction right here. We want to know what its enthalpy change is. We've found these in a book. And now we want to look at, well, how do we combine those to get what we need? Okay? So the first thing we want to do is we want to look at what side do things need to be on. Well, here I've got carbon on the left, and up here I had carbon on the left. So I'm going to keep this one going just the way it is. I have oxygen, I want that on the left. Up here I have it in two different places, so I'm not going to worry about that. I'm going to hope that oxygen will work itself out because it's in two different places. Here I have CO on the right. Here I have CO on the left. So I need to switch directions of this reaction. When I switch directions of the reaction, I also need to change the sign. So it's no longer negative 283.0 because I've switched the direction, so now it's positive 283.0. Then I check to make sure I have the right numbers. I want one carbon. I've got one carbon. I want one CO. I've got one CO. I want a half an O2. Now that means half a mole, not half a molecule. I have not a half, but again, I'm going to hope it works out because it's in two different places. Now, when I add these two things together, okay, CO2 is on the right in the first reaction and on the left in the second reaction, so it cancels out with itself. Okay? I have one O2 on the left and I have a half O2 on the right. This half O2 cancels out half of that one, so I'm left with just a half. So when I'm all done, the carbon carries down, half an O2 carries down, and a CO carries down. And then all I have to do is add up the two things. Okay? So I take my negative 393.5 and I add my 283 to it. All right? So that will give me, once I put those two things together, that will give me what the overall delta H is. So here's one that you can try, but you could also just wait and remind me to try it together in class tomorrow. I'll forget, believe me. And that's all we need to know to start off with thermochemistry, and believe me, there will be more to come about calorimetry later on.